Hi viewers, in this lecture we are going to see the energy conversion devices which we are going to see in the electrical machine subject. Energy conversion devices. First one is electric generator. As the name itself shows that which generates electrical energy is known as electric generator. Okay, which generates electrical energy is known as electrical generator. In a formal way, we write the electrical generator definition as machine which converts mechanical energy into electrical energy in the presence of magnetic field. Okay, this is the statement for the electric generator. Machine which converts mechanical energy into electrical energy in the presence of magnetic field. In the previous lecture, we already seen that how we can induce the voltage or induce EMF in the presence of magnetic field with respect to the Faraday's laws. Okay, Faraday's first law. With respect to the Faraday's first law, we have seen how the EMF is induced. Electric generator works based on Faraday's law of electromagnetic induction. Okay, electric generator works based on Faraday's law of electromagnetic induction. Let us see in brief what is Faraday's law of electromagnetic induction, how we produce the EMF. Okay, how we induce the EMF. Let us see with the example. Okay, take a conductor of length L. Okay, take a conductor of length L. It is moving with a velocity. It is moving with a velocity v. Okay, take a conductor of length L, make it to rotate. Okay, with a velocity v. In the magnetic field, with a flux density of v. Okay, take a conductor of length L, make it to move with a velocity v. Place the conductor in the magnetic field. See, let us see this. Okay, north pole, south pole. Okay, this is the field, magnetic field. Place a conductor here. Okay, it is moving with a velocity v in the clockwise direction. This conductor length, okay, this conductor length, take it as L. Okay, conductor has two sides. See, this is the conductor. Okay, we are seeing this front part. Okay, this we are seeing in here. This is the front part. This is the length of the conductor. Okay, we are taking this one. Okay, we are taking this length. Conductor is moving with a velocity v in the presence of magnetic field. This magnetic field flux density we take it as a B. Okay. Whenever conductor is rotating, whenever conductor is rotating with the help of external devices, okay, conductor we are moving like this with the external devices, it cuts the magnetic field or magnetic flux. See, how we are seeing means first the conductor will touch this flux line, and next the conductor will touch this flux line, and next it will touch this flux line. So conductor is cutting the flux. Okay, conductor is cutting the flux. When the conductor is cutting the flux, an EMF is induced. An EMF is induced. This we say the Faraday's law of electromagnetic induction. This is known as the Faraday's first law also. Okay, this is Faraday's first law. When a conductor cuts the magnetic flux, an EMF is induced. This is Faraday's law. Generator works on the principle of Faraday's law of electromagnetic induction. The magnitude of this dynamically induced EMF is E is equal to BLV sin theta. Here the conductor is rotating and the magnetic field is stationary. Okay. In the electric generator, conductor rotating, magnetic field stationary. Okay. This is the magnitude of the induced EMF. This is the brief explanation for the electric generator. Let us see that. Before going to see the electric motor, let us see how the mechanical energy is converted into mechanical energy is converted into electrical energy with this formula. Okay, we are considering conductor length L with the velocity, conductor is moving with a velocity V, and flux density B. See here, we are considering these three, and this is the magnitude of the induced EMF. Velocity V, it is rotating with a velocity V. This is mechanical energy. E, induced EMF. When the EMF is induced, we get the current. So this is the electrical energy. This is also one way to justify how the electric generator converts mechanical energy into electrical energy. Now let us see the electrical motor. There are two types of electric generator. There are two types of electric generator. First one, AC generator. Second one, DC generator. AC generator produces AC current using slip rings. Okay. AC generator produces AC current using slip rings. DC generator produces DC current using commutators. These are the two types of electric generators. We get into brief in the further lectures. Okay. Now let us see the electric motor. It is also a machine which converts electrical energy into mechanical energy, mechanical energy in the presence of magnetic field. Okay, in the electric generator we converts mechanical energy into electrical energy. Electric motor we converts electrical energy into the mechanical energy. It works based on Lorentz force equation. Okay, it works based on Lorentz force equation. Let us see what is Lorentz force equation. Consider a conductor carrying a current I. Conductor carrying current I. Okay. Consider a conductor carrying current I. Consider a magnetic field with a flux density B. Flux density B. When we place this current carrying conductor in the magnetic field, means in with respect to the flux density, a force is experienced in the conductor. Okay, force is experienced. Consider two poles. Okay, flux lines. Place a conductor which is carrying current. Place a conductor which is carrying current. When we place a conductor carrying current in the magnetic field, it will experience force on it. It will experience force on it. Force is nothing but which makes to rotate. Sorry, which makes to move. Force is nothing but which makes to move continuously. If it is in a circular motion, we call it as a torque. Okay, force in the straight line we call it as a force. If it is moving in a circular direction, we call it as a torque. Here the conductor is moving in a circular direction. Torque, we can call it as a torque is developed. The formula for the force is F is equal to BIL sin theta. Here we are considering length I and the flux density. I is the electrical energy. I is the electrical energy. Here force is the mechanical energy. Force is the mechanical energy. This is how we can justify with the formula that electrical energy is converted into the mechanical energy for the electrical motor. Okay. There are two types of electric motors. There are two types. First one is AC motor. Second one is DC motor. AC motor which takes AC current, which takes AC current, which takes AC current to produce mechanical energy is called AC motor. DC motor which takes DC current, which takes DC current to produce mechanical energy. To produce mechanical energy is called DC motor, and AC motor which takes AC current. This is brief explanation for the electric motor. Let us see the third device, that is transformer. We cannot call transformer as a machine since it has no rotating parts. Electric generator and electric motor, we can call them as a machines because they have the rotating parts, but the transformer Transformer cannot call it as a machine. We can call it as a device because it has no rotating parts. Okay. Transformer is a device which makes to transfer the electrical energy from one circuit to another circuit. Okay. Device which transfer electrical energy from one circuit to another circuit. It does not produce electricity. It only changes the voltage levels, okay, which transfers only electrical energy. Transfers only electrical energy. It does not produce any electricity, okay. It does not produce electricity. It can only transfer. It can only transfer the electrical energy from high level to low level or low level to high level. It only transfers from high voltage to low voltage, high voltage to low voltage, or low voltage to high voltage. Which transfers from high voltage to low voltage called step down transformer. Okay, this is a short form of the transformer. Okay, which transfers from low voltage to high voltage is called a step up transformer. This transformer works based on Faraday's second law of electromagnetic induction. Okay, Faraday's second law of electromagnetic induction. We have already seen the Faraday's laws. Okay, we know that Faraday's second law formula is induced EMF is directly proportional to the rate of change of magnetic flux. Rate of change of magnetic flux, E is directly proportional to the d phi by dt. Okay, the units are volts per turn. Okay, volts per turn. Let us see how we can justify this. Okay, take a coil. Okay, take a coil, place it in a time varying magnetic field. Place in a time varying magnetic field. We know that according to Faraday's law, anything the movement will occur the induced EMF. Here the movement takes place in the magnetic flux. Okay, here the movement takes place in the magnetic flux. Conductor is not moving. Conductor is not moving. Conductor is stationary. Flux is moving. Means varying flux. Flux is varying. In the transformer, flux is varying, conductor is stationary. Okay. From this we can produce the EMF. When the flux is varying, AC flux we are taking, the conductor cuts the magnetic flux. Therefore, the EMF is induced. There should be a movement to induce EMF. This is how in the transformer we can get the magnetic flux. Sorry, we can get the voltage. Okay, induced EMF we can get, and this is the formula for the induced EMF to derive in the further lecture. When we take the magnitude of the induced EMF, we can write it as a N d phi by dt. Here N is the number of turns in the coil. Okay, this is volt per turn. Units are volt per turn. Here the units are volts. because we have already mentioned here tons, number of tons n we have already mentioned here. Magnitude of the induced EMF is n into d phi by dt. In the next lecture, we can see the types of induced EMFs. Okay, thank you.